Welcome to electrostatic discharge. See it, believe it, control it. This program has been developed to provide you with new insights into the sources of ESD damage and methods of ESD control. Recent case histories in manufacturing facilities across North America indicate that ESD damage continues to be a major source of lost revenues throughout the industry. Terry Welsher of Lucent Technologies has suggested that recent experience indicates a 1 in 10,000 probability of 500 volts ESD events in a well-controlled facility, with possibly a 1 in 1,000 probability of 200 volt events. Devices having damage thresholds well below 200 volts are now common in the industry. As component geometry continues to shrink, component sensitivity increases. Failures caused by ESD events could cost a large firm in the neighborhood of $10 million per year in lost productivity and lost customers. To help us understand some of the myths and realities of electrostatic discharge and control, Ted Dangelmeyer of Lucent Technologies will show us a number of demonstrations. Here's Ted.
The ESD event demonstrations that you're about to see have proven to be the most significant training breakthrough that I've seen in 20 years. You will actually be able to see events as low as 50 volts occur in real time. It has been an effective training tool not only for entrance-level employees, but also PhDs in the lab. The detection equipment is also a technological breakthrough and greatly enhances and simplifies the ability to analyze sophisticated automation equipment in the manufacturing process, as well as a tool in the design of new technologies and products.
Ted will use the following special equipment to carry out the demonstrations. This is a gigahertz range oscilloscope. Attached to the input of the scope is a loop antenna designed to detect 1 gigahertz radio frequencies. As Ted charges a metal disc and discharges it against a metal plate, the electromagnetic energy radiated from the ESD event causes a flash of light on the oscilloscope screen. This allows us to see ESD events in real time. When the display is full scale, this indicates an ESD event of approximately 1,000 volts.
I'd like to emphasize that this detector is a very sensitive instrument and is capable of detecting the electromagnetic fields at substantial distance. If I were to walk across the room and touch the doorknob even 50 or 100 feet away, it would still detect the event. To illustrate that, I'm going to charge this disc again and touch it to the corner of the desk, and you'll see an event occurs. And again, even if I were on the other side of the room, the same event would be detected.
In addition to the metal disc that Ted has just used, there is also a disc made of plastic. Each has an insulating handle. The discs are charged by rubbing them on a plastic sheet. The insulated handle keeps the charge from transferring to or from the demonstrator. The wire on the metal disc is attached to a light tower, which shows the actual voltage relative to ground that's on the metal disc at any given time.
But can you charge both insulators and conductors?
Well, clearly the metal disc can be charged by rubbing it on the plastic sheet. The light tower displays about 1,500 volts. The plastic disc can be seen to have a similar charge by rubbing it on the charging sheet and bringing it close to the metal disc. Another device we can use to show the charge on the discs is a static field meter, sometimes called a static locator. The static locator shows the field emanating from a charged object as a voltage. Let's charge the metal disc and view the result on the meter. You can see that the meter shows a substantial charge on the metal disc. Ted repeats this using the plastic disc, with a similar result. The blue material is a static dissipative mat which is connected to ground through a common point ground connector and ground wire. At the right end of the dissipative mat is a metal plate, which is also connected to the common point ground. A wrist strap and tester complete the equipment. Ted tests the wrist strap for functionality. The tone and green light indicate the wrist strap is working correctly. Ted will connect the wrist strap to the common point ground.
Why is the wrist strap so important in ESD control?
Ted will use the ESD demonstration equipment to demonstrate the effects of common activities with and without a wrist strap.
There's a tendency to assume that using touch ground procedures can be effective. In reality, it is not. And to demonstrate that, what I want to show you is by shuffling my feet, I can generate enough charge to trigger an event when I touch the plate. I will continue doing this until it stops. Now it appears as though I'm no longer charged. What do you think will happen when I lift my foot and touch the plate again? You see another event has taken place, illustrating that even though I had touched ground several times, in fact until there appeared to be no charge left, by simply lifting one foot and touching the metal plate again, I was able to generate over 1,500 volts. And clearly, these touch ground procedures are ineffective, even for engineers.
Now Ted is going to repeat the demonstration, but this time he will wear a wrist strap.
I'll put on the wrist strap, shuffle my feet, and the question is, will the events occur or take place when I touch the plate while I'm wearing this wrist strap? Clearly the answer is no, they do not occur. How about now if I lift my foot? Will an event occur or not? No, it doesn't occur here either, and therefore it illustrates very clearly that the wrist strap is highly effective in removing charge and preventing charge accumulation.
Using a wrist strap is only one of the necessary control procedures to lower the incidence of ESD events, right?
Right. In this section, Ted will demonstrate some characteristics of safe and unsafe work surfaces. For this demonstration, Ted has set up the dissipative mat together with a grounded metal plate and a sheet of paper, such as you might require for process instructions or other workplace documents. First, he charges the metal disc as before and touches it to the metal plate. The event detector flashes, indicating a strong electrostatic discharge. This is something to be avoided in the workplace.
Is this event occurring because the metal plate is grounded?
To test this assumption, Ted disconnects the metal plate grounding cord from the common point ground connection. With the metal plate resting on the dissipative mat, Ted again touches the charged disc to the plate.
And will or will not the event occur? Yes, it does occur, even though the plate is resting on this dissipative surface. The event still occurs.
Ted now moves the plate completely off the mat and onto the desktop.
The plate is now completely isolated from ground. Will an ESD event occur?
Now, with this plate completely isolated from ground, no wires attached, it's not resting on the dissipative mat, will or will not the ESD event occur when I take a charged disc and place it on top of the metal plate? And it clearly does. And the reason for that is that the charge transfers from one conductor to another conductor regardless of how it's grounded. It's comparable to two capacitors coming in contact. Again, one charged and one not charged. The charge is shared and the event occurs.
From this series of demonstrations, it is clear that metal-to-metal contact must be avoided, and that conductive work surfaces are definitely unsafe, grounded or not. We'll reconnect the metal plate to the common point ground and look more carefully at the properties of the dissipative mat.
If I take this same charging mechanism and place it on the dissipative surface, will I or will I not see an event? And you notice there is no event when I do that. And furthermore, if I take it over here and put it on the metal plate, there will still be no event. And the reason for that is that the dissipative surface has completely and safely removed the charge.
So the static dissipative mat safely discharges the charged conductor without causing an ESD event. But we must be careful not to interfere with its dissipative role through careless actions. Ted illustrates.
If I go through that same procedure by charging the disc, bringing it over here to the paper, and then back to the plate, will we have an event or not? Yes, we do. Why do we? Because the paper acted as an insulator and prevented the safe removal of the charge from the disk to the mat. So therefore, when you're working with components that are sensitive or assemblies that are sensitive, make sure that the surfaces you use are static dissipative, as you see here. Always avoid metal-to-metal contact and insulators or static generators in the workplace.
Totes are commonly used for transporting circuit cards on the factory floor. In the next series of demonstrations, Ted shows the use of totes and may surprise you with some unexpected results.
Now here we have our circuit board again, and in this instance we have a metal tote tray, highly conductive, and as with the metal plate on the workstation, poses a significant threat. If you take the circuit board, charge it, and place it on the edge of the tote tray, you get an event. And therefore, it's not permitted to have circuit boards resting on the edges or sides of a container like this. Now, is it safe to use such a container? Well, what will happen if we place it inside the container? You'll notice that no event occurs. And the reason for that is that the edge of many circuit cards, not all, but many circuit cards, has a space that is free of the conductive elements of the board. Therefore, when you place it into a container in the slotted grooves, it can be done safely without allowing any ESD discharges to take place.
But what about black totes? Are they safe?
Ted will test this one.
Let me illustrate what happens when you take a charged circuit board and place it on the rim of a conductive container. Even though this is a black material and has some resistance to it, it is too conductive and therefore poses a risk. As a result, one might set a policy in place where you always avoid resting boards on the edges or rims of containers like this, and use the inner slots to contain the boards in a manner that will prevent that discharge from occurring.
So, some critical rules in the use of totes are: don't rest circuit cards on the top or sides of the tote. Slide the circuit card into the slots provided so that only the unmetallized edges are in direct contact with the tote. And don't assume a material is static dissipative just because it is black.
Also, you sometimes need to carry a circuit card a short distance without enclosing it in a tote. You may have seen people carrying circuit cards using a dissipative or conductive bag wrapped around the end of the card in what is called the pot holder method.
Is this pot holder method of transporting circuit cards a safe practice?
If you are not properly grounded as you move with the circuit card, charge builds up on your body. Some of this charge passes through the dissipative bag to the circuit card so that the card itself becomes charged. When the card is handed off, there is a large ESD event. The recipient is wearing a wrist strap, but his body is a sink for the excess charge that has developed on the board. The only safe way to carry the board is by enclosing it completely inside the bag. In this way, the charge remains on the outside. When the bag is handed off, the charge is safely drained without causing an ESD event. We have seen some examples where charge on a circuit board discharges directly to a tote or other conductive surface. ESD that involves charge on a device rather than charge on personnel follows the charged device model in its behavior. Devices such as these IC chips can build up and discharge static in a number of ways. In this case, the parts are sliding in a defective shipping tube. This results in triboelectric charging. As the parts collide with one another, multiple ESD events occur, as we can see on the scope. This type of electrostatic discharge can be very damaging, even though the charges involved are very small. Because the events involve metal-to-metal contact with negligible resistance, the discharge occurs extremely rapidly, resulting in very high current densities. Devices that contact metal parts of machinery, in a placement machine for example, can be destroyed by the charge they are carrying. Look at the events we get when these parts contact this metal plate. Triboelectric charging is one way a device or circuit card could become charged. Charging by induction is another.
Is it possible to damage a component while you are working at a proven good workstation and wearing a wrist strap?
And here we've established that we have a dissipative mat that's properly grounded through this wire. We also have a wrist strap that works effectively and is plugged into the same ground. Here in the center of the mat we have a simple test fixture, and in the socket is a bipolar component that we are going to try to damage in a moment. These wires run to a standard multimeter here that is set up to measure the input resistance of that component. And you'll see on the meter that there is a number 1 displayed indicating a high input resistance at this point. Now, to cause failure, what I'm going to do is move the fixture out of the way and bring into the workplace an insulator. I'm going to charge the insulator with this cotton cloth to create a static field and simulate activity that should not be taking place at a workstation. Now, what I will do is bring the fixture back into the workstation, place it on top of the insulator, and then touch that sensitive junction.
Note that the meter reading has dropped to about 0.3 megohms. You also hear the tone, an indication that the device failure definitely is catastrophic.
Is this ESD damage always catastrophic?
Let's continue with the demonstration.
Okay, now we're going to repeat that demonstration to see if we can create partial damage instead of the full catastrophic failure that we just saw a minute ago. In this instance, the meter will change reading from the one that you see displayed now to a value lower than that, but you will not hear the tone of the meter if we experience the partial damage. So again, I'm going to rub the surface of the insulator and then bring the fixture in place, like so. I'm going to touch this lead in the corner, and you see from the display in the meter that in fact the reading has shifted and we did not hear the tone in the meter. Therefore, the device has been partially damaged and is subject to failure later on in the hands of your customers in the form of a latent failure.
So, the charged insulator produced an electric field that created a potential difference across the fixture and component. When Ted contacted the lead connected to the sensitive junction, this potential difference resulted in the rapid discharge typical of a CDM, or Charged Device Model event. The presence of the charged insulator was the root cause of the damage. It is clear that unnecessary insulators brought into the workplace are a hazard because they can charge devices and circuit boards by induction. This ordinary plastic bag easily generates a potential of several hundred volts. If we repeat the test with a piece of styrofoam, we see the same effect. When Ted brings the charged insulator near the board while grounding the board against the metal plate, the event detector shows that high voltage ESD events are occurring. This is ESD by induction. Remember that Ted caused device failure at the workstation even though the surface was dissipative and he was using a wrist strap.
So we should keep unnecessary insulators out of the workplace. But can we make an insulator safe by grounding it?
Let's try that. We know that if we charge a metal plate and then touch it to a conductive or dissipative surface, all of the charge will be drained away. Now Ted repeats this using the plastic disc. He charges the disc and tests the potential. Then he places it on the dissipative mat. The result is very different. Contact with the dissipative mat does not drain the charge from the insulator. The voltage potential remains dangerously high.
We have just demonstrated that grounding does not discharge insulators. So when insulators are necessary in the workplace, is there another way to discharge them?
Ted will demonstrate an alternative approach with assistance from Larry Snow. For this demonstration, Larry unwinds a strip of Kapton tape, a type of tape frequently used for masking circuit boards before soldering. The light tower shows that the tape is charged to a high potential. When Larry moves the charged tape close to the circuit card and Ted taps the board against the metal plate, you can see several large ESD events. If the tape is held steady, these events soon stop. Now Larry removes the tape, and Ted again taps the board on the metal plate. There is another event. This is called secondary discharge, or double jeopardy. Larry now holds the charged tape in front of an air ionizer. The ionizer is designed to flood the air with both positive and negative ions. The charged tape attracts ions of the opposite charge from this airstream. This neutralizes the charge on the tape. Now, as Larry brings the tape close to the circuit card, there are no further events.
Well, as Ted promised at the beginning, this really is a training and learning breakthrough.
Yes, we learned a great deal by being able to see the events occurring in real time. The equipment illustrates graphically what can happen if you fail to follow proper procedures.
Conversely, if you follow the proper procedures, ESD events do not occur and the product can be very well protected.
Right. Follow all of the procedures that are written as written. Do not improvise, and you'll be fine.